Welcome to Callous Coder, and today we're comparing a NodeJS with a C++ web service. Motherfucker! So I was interested on how different the performance was between the C++ microservice and the NodeJS microservice. Now what they do is they just query a SQLite table. It's the same file that we're using. And it is a table with one single record, and we're querying on the primary key. So there is no flaky stuff going on with weird indexes or anything. So all intents and purposes we're querying the same thing. We're running this query. We want to find the challenge number 1. We do that in all the tests because that's the only record in there. And we want it returned as a JSON object. That's a SQLite thing. So this is the JavaScript version. Let's have a brief look at the C++ version. There we go. So we're doing the same query, as you can see. I cut it up in 2 lines for readability over here. And this is the search, and we do the same search. Sure, this one has other methods implemented as well. So if anything, that would hinder it, but it doesn't work like that in C++ because we're only calling that same root, so that's okay. I'm running it here on port 8182, that is the NodeJS version. And in the background as a service, as a daemon, I'm running the P80 score. This is the C++ one, and it's on 8181. And I'm currently running with 12 threads because this is a 6-core machine with 12 threads. So theoretically that would be the fastest. Although we are I/O bound here, we're not CPU bound, so this may work against us. But let's jump in a couple of tests and see what is happening. I'm running API-B. I'm doing a concurrency of 10 threads, and we're pushing for 30 seconds, so we get a nice average. We'll first do the 8181. I'm also going to run a second shell because I had to tweak something in the kernel for pstars.io to work properly. pstars.io doesn't reuse the time waits automatically. So I had to force the kernel to actually reuse the time wait sockets. Now we have, on any TCP stack, we only have client sockets available from port 1024 up to 65,536, 65536. Well, 64K. What we currently have available, maybe... Oh, we don't have that many available. We have how much available is this? Echo... 28,000 sockets. That may be a limiting factor, but we'll see. And otherwise we will do some TCP IP stack tweaking. Then you learn something cool on Unix as well. I did a lot of IP stack tweaking in my days at IBM when we did the Nokia game. We hosted the Nokia game, a big game 20 years ago, online game, and we moved away from AIX. We moved onto Linux systems with PostgreSQL, Postfix SMTP. We tweaked the hell out of these kernels, and we did things that couldn't be done with AIX even. So there we're done. Wow, 449,000 requests. We have 78 dropped results. This is probably because pstars.io didn't close it, or there were no sockets available. We actually see how many sockets we were, because I had a script running. No, I didn't have a script running. No, I didn't have a script running, but we have a script here. We have 25,000 sockets currently in use. Okay. What this script does, it calls a net stat every 2 seconds, and I look for the time wait state sockets. So these are the time wait sockets, and these are basically occupied. Technically, you're not allowed to use them. The reason is that TCP, back in the olden days when we had slow lines, when you closed the port, it would wait until the last final packet arrived, and that would stay like this for 60 seconds, I believe the default was. These days it's 30 seconds, but this syscontrol that I showed you before, this TCP TW reuse equals 1 allows me to reuse these sockets. So I'm not really running out of sockets basically, as long as they're in time wait. But we need to wait until these are declared before we do the other test, otherwise we're skewing the tests. So now we're going to run this on 8082, that is the NodeJS. So let's see what's happening now. NodeJS should be a bit slower. Let's see how many sockets this one opens. Oh, it doesn't allow to go into time wait, so it closes the socket and actually... Okay, that's a double close. Okay, yeah. And we're done. And what do we do? 296,000. And yeah, we only have one connection open, unlike we saw here. We just open them up. I need to look into pistache.io how I can close this directly and firmly. Maybe I'm missing an option. But yeah, okay. Now, in order to make things fair and compare, I need to run this with 2 threads. One is the listener, one is the worker. And then I mimic Node.js as closely as possible. So we're throwing 15,000 sockets away. That is quick. Where is my top? There's my top. We're now at 158%, and we are only using 3 megabytes of memory. Try that with Node.js. 4 megabytes, there we go, okay. 4 megabyte resident, and we're done, and we have much to my amazement, we have the same amount of requests in 30 seconds and per second. And the reason for that is probably because we are I/O bound and not CPU bound. Yes, multi-threading works, but it's more for CPU intensive things where you're waiting for the same IP stack, the same file, the same NIC for the same file. It doesn't really do a lot. So it is understandable, yeah. Okay. That's amazing. And we are, I said how much was the memory? Grab P80. PMAP-X and your PID. That is something that every programmer should know. 5 megabytes. 5 megabytes of memory. Let's see what the Node does. Around 90, I think. PMAP. 80 megabytes. So imagine this, if you have a Docker swarm or a Kubernetes swarm, you spawn many of these things, many of these processes to allow more concurrency. You are, if you spawn for say 10 of them, you're wasting 800 megabytes on Node.js and only, what is it, 60 megabytes on C++. And the C++ does 400,000 requests and Node.js does 200,000 requests. So that is really, for big organizations, it's starting to pay off dividends to do it in C++. Let's see something. Because we probably seeing that we are, where is it? I had a script running, and that's that. Oh, here. Let's change this for a second to see if we have things in the fin-wait state. Let's do fin. So we have two values. And let's run it again on the C++, because there's not a lot we can do with the Node.js to speed it up. Seems to be the case, 400,000. But we do seem to hit the max on the sockets. So what I'm going to try is set the sockets. What are the current, what was the current range again? 32,000 to 61,000. Let's set that from 10,000 to 61,000. See if that makes a difference. Of course, I'm not allowed to do that. If you do it like this with the syscontrol, it is only done on runtime in the kernel. If you want to save this in the kernel, you have to put them in this syscontrol file on the bottom. Let's see if this makes a difference. Let's run the netstat again. We're clean. Oh, it does do a lot. Look at that. So tweaking the amount of sockets available, client sockets available, makes a massive difference for, in this case, pistache.io, which is the underlying library that does the REST API. Wow. Wow. Let's see what the load is then. It shouldn't make a difference on the load. So it can actually load up more. I got 2 threads running. So it's not really only the listener. The listener does also apparently do work. I figured it was because the code examples always use 2 threads. That one was the listener, one is the worker. But apparently the listener does more. We're at 200. And we now have still resonant 4 megabytes. And we're still hitting 650,000 hits in 30 seconds. So 21,000 hits a second. Unbelievable. Let us first check what this does for Node.js. It shouldn't do anything for Node.js, seeing that it only basically uses 2 open connections the whole time. These are Netflix workloads. No, see? 290,000. Still 9,900 a second. So that doesn't help JavaScript or Node.js whatsoever, as I figured it wouldn't. But let's kill this. And let's now let's do 6 threads, so that we have CPU only, and we can utilize cache as well. It's running. Oh, we slowed down. With more threads, we slow down, so we're definitely I/O bound. Now I'm very curious. We saw that the threads. Now I'm curious if I just run one thread, if it will crash or. We see that we're basically networking, network RX receiving. I think this is the I/O that we're bound. We're not really blocking. That is a good thing. So with a single thread we're on 431,000. And what were we on a single thread on? 300,000. So 30% quicker. That is interesting. So let's run it again with IO stat as well. So we're monitoring the CPU here, and we see that it's basically net bound, which you would expect. And IO stat measures the disk access. And this is on the SDA, I know that, because it's on my home drive, that is the slow drive. So we shouldn't see a lot of disk I/O. You see a write every now and then. That is the journal that's being written on SQLite. But yeah, we're not blocking anything significant. So the I/O bound is sheer network. Two threads is the most optimum for peace-touch.io. Interesting. So in conclusion, these are interesting findings. Yes, the TCP version is 200% faster than NodeJS, but NodeJS actually does pretty well with around 10,000 requests a second on a laptop, on a Core i7 9th generation. It's actually really insane. We did see that we are I/O bound, which was to be expected. That's why 2 threads on my C++ application delivered the most performance, doing 650,000 requests in 30 seconds. Insane numbers. These are not normal workloads by any stretch of the imagination. These are Netflix and Amazon workloads. What else? Yes, memory. Now I was shocked to see how much memory Node.js actually used. 90 megabytes resident. Imagine creating a Docker swarm with 10 instances. You're already pushing a gig there. That is insane. Whereas my C++ application, 6 megabytes resident. I mean, those are numbers that make me happy. But generally, when you're not memory bound, you're not really chasing these high, insane workloads, Node.js actually is really fine. And I think that Node.js may actually outperform .NET Core. But we will have to see that in another video. But yeah, I'm impressed with this. But it also shows that when you're having web services and web service, that tuning your IP stack, or TCP stack to be specific, does pay diligence. Increasing the number of client sockets, just do that, make that standard. Reusing your time await socket, just do that, makes sense. So yeah, I think that is the conclusion for now. I hope you learned something. This was a very technical video, more technical than usual even. But these are the things that I really like and really dig. So I hope to see you in the next one.